All right, hello everyone. So what I'm going to do in this video is I'm going to cover the rest of chapter 21 that we didn't cover on the recitation sheet. So if you guys just want to follow along, and I'm going to cover the entirety of the chapter 20 recitation sheet. What I would recommend if you're watching this video is just cover the parts on chapter 20 that are actually covered in lecture on Tuesday. Those that aren't shouldn't be covered on the test, so you don't necessarily have to cover the whole thing if not everything is lectured on Tuesday. So we'll go ahead and pick it up. In recitation, let me look through the ones we covered. I think we covered this one. We covered this one. And we covered this one at the bottom. All right, so we'll work through these. So again, doing basically retrosyntheses and forward syntheses with condensations, right? And there's all sorts of names for each of these. There's Claisen condensations, there's Dieckmann condensations, there's Aldol condensations. There's so many names, it's very easy to get tripped up, but don't get overly caught in that. It's simply just nucleophile and electrophile. And your nucleophile is always going to be the carbons that are alpha to your carbonyls, right? So those alpha carbons that bear protons, right, those can get deprotonated and form an enolate, rendering those alpha carbons as the nucleophiles. And obviously your carbonyl carbons are going to be your electrophiles. So in this case right here, what we have, right, we have this molecule right here. Let this come into focus. We have an ethyl ester, right? We have a ketone. We're reacting it with ethoxide followed by protic workup. So what that tells you is, well, when you have ethoxide, right, that's a base. That's a strong base, right? And we just so have this alpha carbon right here has an alpha proton. This strong base can take that proton and form an enolate. So that enolate is going to then render this carbon nucleophilic. All right, so I'll just draw a lone pair. The real resonance structure looks more like this, right? Obviously, you'd have, right, your enolate. That's what it would really look like. But the principle is the same. This carbon is going to be your nucleophile. So this is going to attack right here at your electrophile. That is the ester, right? That's going to temporarily form a tetrahedral intermediate, right? And alkoxide up here. Those pi electrons are going to kick back down, simultaneously kicking off the ethoxide. And you can imagine what that's going to do. That's then going to form a ring, right? And if you count your carbons, right, you have 1, 2, 3, 4, 5. There's 5 carbons in this ring. So therefore, we're forming a 5-membered ring, and it's going to retain, notice with the esters, when you kick off an ethoxy or a methoxy, right, you're going to retain the keto configuration. You're going to retain that carbonyl. It's not going to get reduced. So let's draw it, right? So we have this 5-membered ring originally. So that's not going to leave. We formed a new 5-membered ring. We have a keto right there, isopropyl right here, because we have an isopropyl right here. And we also have a ketone group right here, right? So this is what we get. We already covered this one, so I'm not going to go through that. Here we have a retrosynthesis, right? And a lot of times with these, we'll have different possibilities. And so let's look at this molecule, and let's look at how many different ways can we cut it, and how many different starting materials can we have. So I already see the first possibility right here, right? If you notice, we can have a possibility here where we cut right here. In that case, your nucleophile would obviously have to be, this is a CH2 group. This would have to be diethyl carbonate. So let's draw that. And you'll see the logic as to why that is. So I'll draw that out. So again, the 6-member ring, that's not changing. So we have a methyl here, we have a hydroxy here, that's not going to change. And OET, carbonyl, plus when I say diethyl carbonate, right, that looks like this. Right, carbonate's a CO3 group. It's got a carbonyl flanked by 2 oxygens, right? That's a carbonate group. When we say diethyl carbonate, that means on either side, these oxygens are bonded to ethyl groups. So anyways, obviously, so when we look at this, okay, why does this work, right? Well, if you react it with a strong base, right, once again, that's going to form an enolate right here. I'm not going to draw the structure of an enolate, but I'm going to draw these lone pairs just for reference. This carbon is going to be your nucleophilic carbon, right? That's going to attack right here, form a tetrahedral intermediate, kick down those pi electrons, reform the double bond, kick off the ethoxide. And notice what that's going to form. That's going to link this nucleophile to this electrophile. And when you look right here, that's exactly what you have. You have that nucleophile, you have that electrophilic carbon, bonded to a carbonyl, bonded to a carbonyl, bonded to an ethoxy, bonded to an ethoxy right there. That's one possibility, right? A second possibility, I'll draw a little line to make some space. Second possibility is we can cut right here, right? And actually, that might actually be the same. So actually, this is going to be an interesting case, right? We can cut right here and make this part of the molecule bear the CH2 group. That becomes an enolate. That carbon then becomes nucleophilic. Attacks here, what's going to be, obviously to link this group on, we would need to use a diethyl carbonate as our electrophile. But notice here, right, the cyclohexane ring, CH2, ethyl ester, right? That's the same thing we already have right here. Cyclohexyl group, right? Same substitution right here. We have a CH2 group, ethyl ester group here. It's actually the same structure, so we don't need to draw a second possibility because that possibility is going to be chemically equivalent. It's going to be the same thing as this, even when we cut it this way or that way. So it's actually going to look the exact same. So that's the possibility right there. So here, we're going forward, right? It's a little bit easier to do. We have, this is 3-pentanone, right? And diethyl carbonate. So we have ethoxide followed by protic workup, right? And so, yeah, anyways, this is going to get deprotonated. We're going to form an enolate. I'm not drawing the enolate. I'm just drawing lone pairs in the carbon just for reference, right? But obviously that's going to attack right here. I'm just drawing this as a concerted mechanism. There's some steps in between, but logically, take some time and understand why we attack the carbon center. We form the tetrahedral intermediate. When I say tetrahedral, I mean that this carbon right here, right now, is an sp2 hybridized carbon. And the product, it's going to be an sp2 hybridized carbon because it has a double bond and 2 single bonds. But the intermediate looks like this: ETO, OET, R group, which is basically all this area, alkoxide. I say tetrahedral because in this case, the carbon is sp3 hybridized. So here, I say tetrahedral intermediate, that forms temporarily, right? These pi electrons end up kicking back down, kicking off the ethoxide, and that's this part where these swing around, kick off the ethoxide, right? I'll draw the nucleophile first, right? This is the nucleophile, this is the electrophile, this is the nucleophile, this is the electrophile. The electrophile is bonded to carbonyl, OET. That's what we get. All right. So in the next possibility, or the next problem, we have, this is ethyl butanoate reaction with ethyl benzoate, right? So same thing, we use ethoxide followed by protic workup with acid, right? That's what H2O plus means. So it's like, okay, we see 2 esters, like, okay, well, how do I know it's going to react? Well, first off, let's look at alpha carbons. Okay, then let's look at, okay, which one of those alpha carbons actually bear a proton that can be deprotonated, forming an enolate, which can then render the alpha carbon nucleophilic. Alpha carbon here, alpha carbon there. But notice here, this carbon already has 4 bonds. Okay, this benzene ring, right? This carbon has 2 bonds to carbon right here, 1 bond to carbon there, 1 bond to carbon here. It already has 4 bonds. There are no bonds to protons. There are no alpha protons available to form an enolate. So this has to be our electrophile. It cannot be our nucleophile. Here, though, we have 2 protons available. This can be our nucleophile. And so when we think about mechanistically what's going to happen, we form the enolate. Again, the enolate really looks like this. And what really happens mechanistically is this kicks down, this kicks out and attacks. I'm just drawing this, you know, just for convenience. We have a lone pair here. It's the same thing. This would kick down. This carbon would then attack. This is the nucleophilic carbon. This is then attack the carbon center, form the tetrahedral intermediate. Those pi electrons will then come back down, simultaneously kicking off the ethoxide. And when we draw what that forms, I'll switch it up. This time, let's draw the electrophile first. Then we'll draw the nucleophile. But we have the benzene ring. Right, so we reform the ketone. This is our electrophile, links to the nucleophile. So the nucleophile is this carbon right here. If we look at this carbon, what is it bonded to? Okay, let's keep our orientation proper. It's bonded to an ethyl group. So let's draw that first. Right? Wait. Yeah. It's bonded to an ethyl group. This carbon bonded to an ethyl group. It's also bonded to one bond over an ethyl ester group. So one bond over, here, OET. And notice the resemblance, right? When you think here, 1, 2, 3, 4, oh, you can see where the ethyl butanoate came from. The alpha carbon was deprotonated. That functions as a nucleophile, and that attacked right here, kicked off the ethoxide, and then linked, forming this beta keto ester. And that's what we're forming right here. We already did this problem, so we'll go to the next page. So now we're doing a mechanism for this, right? And these reactions are called a Claisen condensation. That's what we just did on the last page. So now we want to draw a mechanism. We're going to go a little bit more in depth, right? And so we start off with ethoxide. I'll draw my lone pairs here. So what's going to happen first is, obviously, this is a strong base. What is this going to do? It's going to function as a Bronsted-Lowry, right? It's not Lewis. It's not Arrhenius. It's a Bronsted-Lowry base. So it's going to take a proton. Remember your different base definitions. So we have these errors right here. Y'all can see that. What that then forms, notice we have two equivalents here, right? Because we'll see the product, 2 moles of this gives you 1 mole of product. And we'll see that in the end, I'll highlight it. It's OET. Those are the pretty lines, but these lines represent lone pairs. The one here. So this is the enolate. So I've been conveniently just drawing lone pairs on the carbon. This is what actually is the major resonance form. This is the enolate. So what's going to happen next is nucleophile attacking electrophile, right? And the electrophile will simply be the next equivalent. We said we had 2 equivalents of this. Ester. A little bit of naming practice, right? We know when we name esters, right? This is going to be ethyl. And what is it? 1, 2, 3, 4. 3 methyl. So it's going to be ethyl. 3 methyl butanoate. So make sure you all review the naming. That's what we have. So what's going to happen mechanistically, this kicks down here, reforms that carbonyl. That's going to make 5 bonds on this carbon. We can't have that. So these pi electrons then get forced onto this carbon temporarily. They then attack this carbonyl. And I'm not going to draw the swing around, but the arrow goes all the way around, kick the ethoxide. We're going to actually show it step by step. So we're going to show the tetrahedral intermediate here. So let me draw, let's draw the nucleophile first. So we have here, OET. This is our nucleophile. This is our nucleophile. Square of the electrophile. Let's draw that. So this carbon's a square. Let's look at everything this carbon's bound to. Let's keep our orientation straight. So we make an alkoxide, so there should be an alkoxide right here. Okay. There is a bond to OET. There's also a bond to an isobutyl group, as we see right here. Carbon, carbon, carbon. That's not supposed to be a wedge or anything. Let me actually kind of redraw that. Not the most stellar drawing in the world. One, two, three, four. Yeah, it's isobutyl group. So what's going to happen next is we're going to kick off this ethoxide. All right, let me just okay. So next we're going to kick off the ethoxide. So we're going to kick down like this. That's going to form 5 bonds on carbon. We can't have that. So simultaneously, we're going to kick off ethoxide. So that then gives us this. And notice we're not protonating right here because we need to kick this group off. In order to reform this double bond, if we had a proton on that oxygen, that would form an oxonium ion. Right? If we had a proton on this oxygen, it wouldn't be so favorable for these pi electrons to swing back down and reform that double bond, kicking off this ethoxide, because that would form an intermediate that looks like this. That's very, very, very acidic. Very acidic. And notice we're in a basic environment. So pretty much everything we have should be either negatively charged or neutral. We shouldn't be having any positive charges, shouldn't be having any crazy strong acids, because that's not going to happen in strongly basic conditions. I don't know why I drew this methyl group so ridiculously tall, but let's fix that up. Let's draw the rest of this. We have the ketone. Yep, isobutyl. That's what we got. And it makes sense, right? Because we can kind of see right here the electrophilic half that had the OET, how it got kicked off by the nucleophilic equivalent, right? That's why we have 2 equivalents to make one product. But we're not done yet. We have very basic conditions, and what we have right here is a proton that's quite acidic. If you think about the conjugate base of this, right? So let's draw a base. We can use ethoxide. Draw it on either side. Well, I'll draw it on this side. Not that it really matters too much. So what we have is this. I slightly changed the conformation, but it's still the same isobutyl group right here. Oh, wait, well, and this should be an enolate. Notice right here, we took away this proton with the base, we formed an enolate. Now, why that happens is because this proton right here is quite acidic. And we have very strongly basic conditions, so it's going to get deprotonated. The reason it's acidic is because, remember, when we have a proton in between 2 carbonyls, it's going to be quite resonance stabilized. So when we talk about the conjugate base, it's pretty well resonance stabilized. Think about it. We can have a resonance structure where this comes in here, and we can even tautomerize to the other side. It's quite well stabilized both by tautomerizations and by resonance. So especially in basic conditions, we're going to form the enolate. We're not going to be stuck here. But this is what we want. We want this diketone, or not, I should say, beta keto ester as our product. So what we have to do is do a protic workup. So we can react then with an acid, H3O plus. I should say, let's draw the mechanism. Let's say H plus, right? And basically what happens is this. Classic enolate mechanism, we reform the keto. These pi electrons then take the proton, they function as a base. We've seen that before. Pi electrons can function as bases and nucleophiles. We've seen it happen plenty of times in different reactions. Right? And this is what we get. So that's the structure. All right. So the last step is acetoacetic and malonic ester syntheses. And so real quick, I'll go over the basics of it. When it comes to these type of problems, all right, first off, acetoacetic ester synthesis, right? As you'll learn in class today or on Tuesday. So acetoacetic ester synthesis is exactly what it sounds like, right? We start off with acetoacetate, which looks like this. But it's acetoacetic ester. This would be acetoacetic acetate. Acetoacetic ester means that we have an ester, and usually we use like an ethyl ester. So an OET. Malonic ester synthesis, if you remember from Gen Chem 2, when you did the diprotic acid titration, that was with malonic acid. And that's a 3-carbon dicarboxylic acid. But we're using the ester, so we're using an ester derivative. ET. So that's malonic ester synthesis. And so whether we use acetoacetic ester synthesis or malonic ester synthesis, right, the pathway is the same. Basically, you're going to have molecules like this. And what you're doing, it's like, okay, how on earth do you get from this to this, or from this to this, right? So the general pathway of reactions is the exact same. If you look at both of these guys, they have an alpha carbon right here with a proton, as we just saw before, in between 2 carbonyls, which is going to be quite acidic. That then forms an enolate, rendering these middle carbons nucleophilic. And so the whole idea with acetoacetic and malonic ester syntheses is that we form the enolates, and obviously these molecules have 2 different protons available, so they can have 2 successive protonations and 2 successive enolate formations to stick on 2 different alkyl groups. Well, how do we do that? Well, first off, use a base, use sodium methoxide. Let's make an enolate, followed by an alkyl halide, the alkyl group of which you want to attach. So let's say you want to attach an ethyl group right here. Okay, well then you'd use sodium methoxide, followed by ethyl iodide. Let's say after that you want to then attach a cyclohexyl group. Okay, you'd again do sodium methoxide, followed by cyclohexyl bromide or cyclohexyl chloride, right? And then it's like, okay, I want to get rid of one of the carboxyl groups, right? I have this ethyl carboxylate, I don't want it. What we can do is hydrolyze it, followed by a decarboxylation. So how does that happen? Well, we know that, you'll see in chapter 20, that hydrolysis of esters can take place via acidic and basic, or basic conditions. I mean, it happens in both conditions, right? But basic conditions, so saponification, right, of esters with sodium hydroxide is a lot faster kinetically than it is with acid. So it's convenient to use a base like sodium hydroxide OH minus, heat it up maybe a little bit, and that'll give you a basic hydrolysis. That'll take you from your ester to your corresponding carboxylate, right? Your carboxylate, your deprotonated carboxylic acid, right? Carboxylate form. Then we do acidic conditions, protonating that carboxylate to the carboxylic acid and decarboxylating it. And that happens via an interesting mechanism, right? So let's just use a simple example I like to use. Let's say here. I think make sure I'm not butchering this. Okay. Yeah. So it happens we have this, right? So this right here, right, we just saw, this is acetoacetate. This is the acetic acid, right? We have our aceto group, right? Carbon-carbon aceto group. Or no, this is yes, acetate group right here, aceto group right there. And so mechanistically what we have, and the reason I drew it specifically in this orientation is because when we heat this guy up, right, delta T, this is the mechanism. Pi electrons here from the oxygen, take away this proton, right? These electrons then move in here, forming a carbon-oxygen double bond. These electrons move here, right? And think about what that just did. That forms two different things. That forms one, this. What is that? That's carbon dioxide. That's a gas that's going to bubble away. Plus, we'll make this enol. But we know that we can have tautomerization of enols. And usually the keto form is going to be a little more stable. In this case, it's more stable. In the tautomer here, the equilibrium heavily favors the formation of acetone. And so this is what we have. What we have here is that we successfully decarboxylated. So again, let's say you had aceto. We have this, right? We have ethyl acetoacetate, and we want to make acetone. Okay, well, let's do basic hydrolysis. Let's get the carboxylate. Let's then use H3O plus and heat to protonate the carboxylate, get the carboxylic acid, right? And via this mechanism, we decarboxylate it. You get the enol, that tautomerizes heavily to then give you the corresponding ketone. And that's what you have. You successfully decarboxylate. And so let's apply that to these problems. So I'll clear up some room. Okay. All right. So, looking at these things, right? And so with that in mind, right, we can do a decarboxylation. And usually with these acetoacetic and malonic ester syntheses, we are going to have a decarboxylation step. And why that's a good hint is because when you look at these two things, you're not being told whether or not to start, or whether to start with acetoacetic ester or the malonic ester. You're not being told. You have to figure that out. How you figure that out? Okay, well, look how many carboxylate groups you have. Here, we have one carboxylate group. Here, we have none. We know that we're going to do a decarboxylation step, which is only going to get rid of one carboxylic acid, not two. It's only going to get rid of one. So that means when you have one carboxylic acid group or carboxylate group, that means you originally had two because you decarboxylated one. So we had two carboxylate groups in the reactant here. Here, notice how there's a carbonyl, but there's no carboxylate groups. There's no carboxylic acid groups in here. That tells me we started with only one, and we decarboxylated it. Now, what does that tell you? Okay, well, acetoacetic ester versus malonic ester, which one has two carboxylic acids? It's the malonic, right? Malonic acid is a dicarboxylic acid. So that means this one, we already know, because we end up with one carboxylate group, we had to have started with two because there is a decarboxylation step along the way. That means we had to start off with two to get down to one. So we'll draw that. OET. All right, so this is our starting point. It's like, okay, how do you figure this from that? Let's take it one step at a time. Let's look at the carbon that links to the carboxylate group, okay? That's this carbon right here. That's this carbon in the center, okay? Let's break it down. Well, what's attached to it? Cyclohexyl group, ethyl group. That means we need to do 2 successive steps in which we form an enolate and react with a cyclohexyl halide and then with an ethyl halide. Let's do the ethyl first. So we'll use sodium ethoxide as our base, followed by ethyl iodide. You could also use ethyl bromide or ethyl chloride. I'm going to choose ethyl iodide. You need an ethyl halide. And what that's going to do is everything else is going to look pretty similar. But right here, what you've effectively done, oh, let me draw it, not bent. We've installed an ethyl group, okay? What else do we need? We need a cyclohexyl group. Let's do that next. Draw a little arrow here. So let's do, again, sodium ethoxide. And again, what we're doing with sodium ethoxide, we're deprotonating that proton. We're taking it off. We're forming an enolate, rendering this carbon nucleophilic. That then will attack the electrophile, which is, let's do cyclohexyl halide. Let's do a cyclohexyl bromide. Right, so we'll do a cyclohexyl bromide. That then will link a cyclohexyl group right here in place of that proton. All right, because the proton will be taken away by the base. We form the enolate. That enolate, the nucleophilic attacks this electrophile, which then connects the cyclohexyl group. So let's draw what we have. So ETO. Ethyl. All right, so we want to decarboxylate, right? When we look at this, the conformation might look a little different, but look, we have a cyclohexyl group, alpha carbon, ethyl group. It's pretty similar, and then the carboxylate. Difference is here we have 2 carboxylate groups, right? Let's hydrolyze them. Let's do a basic saponification with hydroxide. Let's heat it up a little bit. That then will give you, that's going to hydrolyze both of these, so we'll use excess hydroxide, hydrolyze both of them, giving you carboxylates. So let's draw that. It's going to look like this. O minus. Not a very great looking hexagon, but that's a hexagon right there. And the last step to get to here, I just showed the mechanism earlier, right? This is where you do H3O plus delta T, decarboxylate one of these carboxylic acids. It's only going to decarboxylate one. That'll then leave you with this monocarboxylic acid. And the way we do that, again, is H3O plus delta T. Why would you need H3O plus? So we can protonate these oxygens. And as you remember in that mechanism, if you scroll back a little bit, that involved the carboxylic acid being protonated. So we protonate it, and then we go. So you might ask, if we can do acid catalyzed hydrolysis, why don't we go straight from this to acid catalyzed hydrolysis followed by decarboxylation all in the same step? And the answer is because it's a very slow reaction. We have that basic saponification or hydrolysis of esters occurs much, much, much faster than acid catalyzed hydrolysis. But acid catalyzed decarboxylation is relatively quick when you heat it up. So we do basic hydrolysis first to quickly get this step. Then we do acid catalyzed and obviously heat mediated decarboxylation. All right, that's the step. And the logic is the same for the acetoacetic ester synthesis. And so when we go here, obviously, I made note that there are no carboxylate groups in the product, which means in the reactant, there must have only been one carboxylate group. Well, we know that the malonic ester, right, malonate, has 2 carboxylate groups. But acetoacetic ester only has one. So that's what we're going to start with. Because it only has one carboxylate group in the reactant, when you decarboxylate, you're going to have none in the product, as we have. All right, so the logic's going to be the same. Let's identify our alpha carbon. Let's identify our alpha carbon. It's right here. All right, this isn't the alpha carbon. It is a alpha carbon, but it's not the alpha carbon. All right, it's the carbon right in the middle. That's this one. This is going to link to two different alkyl groups, and we're going to need to install those. So we have an isopropyl group, we have a cyclohexyl group. Let's install this isopropyl group first. So first off, we'll need a base. We'll need like sodium ethoxide. We'll then do isopropyl. Let's do isopropyl bromide, or 2-bromopropane, right? Sodium ethoxide renders this nucleophilic, so it can attack this electrophile via an SN2 reaction. That then links an isopropyl group onto this ethyl acetoacetate unit. So let's draw that. So isopropyl. All right. Next, we need to install a cyclohexyl group. So same thing, we'll do sodium ethoxide, followed by cyclohexyl bromide. What that'll give you looks like that. And notice we're really close in structure to what we have here. We just need to get rid of this carboxylate group. How to do that? Same thing as last time. We'll do basic saponification or basic hydrolysis. Let's use sodium hydroxide. Let's heat it up a little bit. And what we'll get, oh, yeah, it's not going to be gone yet. We then form the carboxylate because we hydrolyze the ester. And we still have the isopropyl group here, cyclohexyl group right there. Last step to get here, you guessed it, H3O plus delta T. All right, that's it for chapter 21.